Unit Overview. In this unit, we will study another fundamental data structure called linked list. Like the arrays, the linked list stores a set of homogeneous data items which have linear relationship. However, linked lists have several performance advantages over the arrays, which make them more suitable for applications requiring frequent insertion and deletion of data elements. The unit begins with an introduction to the concept and architecture of a linked list and associated basic operations. A detailed formulation of algorithms for insertion, deletion, traversal, and sorting is presented. The implementation aspects of the fundamental operations are discussed in depth. The performance issues, advantages, and shortcomings and applications of the linked lists are also covered. The last part of the unit provides a description of different variants of linked list. In particular, characteristics of circular lists, doubly linked list, multilist, the relevant operations are also examined. Important algorithms for handling different kinds of lists are considered together with the programming aspects of fundamental operations. Objectives. After completing this unit, you should be able to understand the basic concepts and architecture of a linked list data structure. Learn about the storage arrangement of data elements of a list. Comprehend the algorithms for insertion, deletion, traversal, and sorting operations. Algorithms using dynamic allocation of storage space. Understand cursor implementation of linked list. Describe relative advantages and disadvantages of linked list data structure. Learn the use of linked list in different applications. Understand the concepts and structure of circular linked list, doubly linked list, and multilist. Learn about the basic operations associated with different forms of the linked list. Understand the implementation aspects of circular and doubly linked lists. Learn about the structure and advantages of multilists. Introduction to linked lists. A linked list, sometimes referred to as singly linked list, is a collection of data elements called nodes. Each node consists of two parts which are called information field and linked field. An information field contains data elements of the same type which can be primitive types such as integers, characters, or real numbers. In some applications such as database, the information pointer may contain complex data types such as records consisting of several data items. In the case, however, one data item called key value uniquely identifies each node in the list. The link field distinguishes a linked list from other data structures such as an array. The link part in a node contains a pointer to the next data element in the list. Actually, it contains the storage address of the successor node. The first data element in the list is referred to as front node or head node. A special pointer called head identifies the front node. The elements of list are normally traversed by first accessing the head pointer and then moving across the list. Sometimes a special node called sentinel is also used, which provides an entry point to the list. It can also contain other useful information about the list such as size of list, structure of a node, and so forth. If the list does not contain any data item, it is referred to as empty list. In an empty list, the head pointer is usually set to null value. The last element in a linked list is called tail node or end node. The link pointer in the tail node contains a symbolic constant null, which is meant to signal the end of the list. In C++, the null value is defined in header file string.h. Other implementations might use different constants, such as -1. In pictorial representation of a linked list, cross might be used to mark the end of the list. In diagrammatical representation, the logical structure of a linked list is shown using a forward-pointing arrow to link together a pair of nodes. Figure shows a typical pictorial of linked list consisting of 5 elements. As mentioned before, a list may be used to store complex data type, such as words in a text block or record in a database. Figure shows 2 such lists. The first structure contains words in dictionary order. The second list consists of student records, with each node containing roll number, name, and subject. The roll number is the key field which uniquely identifies a node. Observe that in the pictorial representation, the arrow points to a succeeding node alone. Later, we shall examine special lists in which the arrows are directed forward and backward. Storage structure of linked list. Storage structure describes the physical arrangement of nodes in computer's memory. Each node, with the exception of the terminal node, contains the memory address of the next linked node. For example, suppose that A and B are 2 nodes in a list, such that they are stored in memory locations 1000 and 2000. If B is a successor to A, then link pointer of A would contain value 2000, that is, the storage address of B. This is schematically shown in figure. Another storage structure for list consisting of records is shown in figure. The second example is particularly illustrative of how nodes of a list might be distributed in the main memory. Observe that successive nodes are not placed in contiguous storage locations. This is in contrast to the storage structure of an array, which consists of a single block of memory with successive cells allocated to array elements. In the case of a linked list, nodes might be scattered in different memory blocks. The link pointer in the nodes identifies the storage location of the successor nodes. Actually, the compiler dynamically allocates the memory space when a new node is added to a linked list. The storage space allocation is made out of a special memory block called heap. A heap is meant to provide storage space in addition to the space utilized by different elements of a program, such as constants, variables, and program statements. During execution of a program, the cells of a heap are recycled. This means that memory cells released by deleted nodes are reallocated to the newly created nodes. In this way, the linked list can be expanded dynamically. There is, however, an upper limit to heap size which depends on the computer system. In order to make efficient use of available heap space, the implementation of deletion algorithm must be designed to release the space occupied by deleted nodes. Operations on linked list. In order to access and process data contained in a linked list, we need to perform some basic operations on the list. Most applications require inserting of new data elements deleting the existing data, printing the contents of a list, or traversing the list to access the contents of nodes. Sometimes we need to sort the list in the alphabetic or numeric order of some key data element. Searching is another important operation which looks for a given data value in the list. Other less frequently used operations include checking the size of a linked list, finding if list is empty, and copying elements of a list in another list. Normally, the operation of checking whether the list is full is not applied, because a linked list can grow dynamically by utilizing the storage space provided by heap. We now examine the implementation of these operations and explore the associated algorithms. The most common approach to implementation of linked list is called pointer method, which stores data in a collection of objects. Another method called cursor implementation uses arrays to store node data and linked pointers. We first discuss the pointer implementation and programming aspects of this approach. Pointer implementations of linked list. In pointer implementation, we define an object called node, which stores the data elements and physical address of the next element. In C++, structure of node can be defined using a class. Figure shows a typical class named node. Observe that the object represented by the class consists of two components. The first field is meant to hold a character string of up to 20 characters. The actual type and size can vary with application. The second field is a node pointer. It holds the address of the successor element. It is a self-referential pointer variable because it points to an object which is of the same type as the node itself, that is, of type node. The members of the class node have been declared public because other classes or their methods would need to access the data contained in node. After having specified the structure of a node, we can define an interface class for the linked list. Figure shows the basic structure of the class called linked list. It contains a private member head, which is meant to point to the first element in the list. In the constructor, it is initialized to null value. Linked list includes these public methods: add new node to the list, remove a node, print the contents of the list, sort the list, search the list, check if list is empty, return the size of the list. Actual implementation of these methods should take care of data types which may be passed as arguments and the data returned by the particular method. We shall examine these aspects when we consider the programming details of these methods. Inserting nodes into linked list. After a list object has been created, a new node can be inserted in the beginning, in the middle, or at the end of the list. Different algorithms are used to handle each of these cases. Let us explore in detail the steps involved in these algorithms. Inserting node at front of list. In order to add node at the front of a list, we create a new node and set its link pointer to point to the pre-existing first node. The front is normally identified by the head pointer. Thus, the head pointer is reset so that it points to the new node. Figure shows an example of a list consisting of 4 nodes containing letters A, B, C and D, to which a new node Z is added at the front. The end of list is marked by a cross. Next figure shows the code fragment for the method insertFront, which accepts a character string for the node value. Create a new node and adjust pointers so that the new node becomes the front pointer. Briefly, it performs these steps. First of all, a new node is created. Then, data is copied into node. Then, set pointer to point to first node. Finally, readjust the head pointer. Inserting a node at end of list. In order to add a node at the tail, we use a pointer which is initially set to point to the first node. Then the list is traversed until the pointer points to the last node. A new node is created and the link part of the tail node of original list is reset to point to new node. Figure shows the steps for inserting a tail node. Next figure shows the code fragment for the method insertEnd, which implements the procedure for inserting a tail node. It performs these steps. First of all, traverse the list. Then, create a new node. Then, copy data into new node. Set linked pointer to null. Finally, set pointer of tail node. Inserting node into the middle of the list. A new node can be inserted into the interior of a linked list which either precedes or succeeds a given node. The insertion algorithm is different for each of these cases. We first examine the case when new node is to be inserted after a given node. As before, we use a temporary pointer to traverse the list until the given node is reached. A new node is created and the linked pointer of the given node is reset to point to the new node. The link pointer of the new node is set to point to the node which is next to the given node. Figure depicts the steps involved in the insertion procedures. A new node, Z, is inserted after the node C. Inserting a node before a given node. The algorithm for inserting a node before a given node is slightly more complex than the node for inserting after a specified node. The reason is that in placing a new node in correct position, we need to readjust the link pointer of the node which is to precede the new node. Thus, we have to identify not only the given node, but also the node that precedes the given node. For this purpose, we use 2 pointers to scan the list. The first pointer is moved to identify the specified node. The second pointer trails immediately before the first pointer. In this way, when the first pointer ultimately reaches the given node, the second pointer points to the preceding node. We can use the second pointer to point to adjust the link pointer of the preceding node to point the new node, and then use the first pointer to reset the pointer of the new node to point to the given node. The procedure for inserting a node before a given node is depicted in figure. As will be seen, a new node Z is inserted before the node C. Observe that 2 pointers are used. One points to C and other to the preceding node B. The code for insertion algorithm is given in the demonstration that follows. Deleting nodes from a linked list. A major advantage of a linked list data structure is that it allows judicious use of storage space. A node which becomes redundant can be purged to release the allocated space. As with the insertion, the deletion operation can also be applied to the front, middle, or last node of a list. The algorithm varies slightly in each case. We now examine these cases separately. Deleting a front node. In order to delete a front node of a list, we create a pointer which is set to identify the first node. The head pointer is then moved to point to the next node. Using the pointer, we remove the first node. Figure illustrates the procedure for deleting the front node of a sample list containing A, B, C, and D. Deleting tail node. For deleting a tail node, we use two pointers so that in traversing the list, the second pointer trail immediately before the first pointer. Thus, at the end of the traversal, the first pointer points to the tail node, and the second pointer points to the node that precedes the tail node. We use the second pointer to set the link pointer of the preceding node to null value, so as to sever its link with the tail node. Then, using the first pointer, we remove the tail node. The deletion procedure is illustrated in figure. Deleting a middle node. The algorithm for deleting a middle node is essentially the same as for deleting a tail node. We use two pointers to scan the list, such that one pointer immediately follows the other. After the given node has been identified by the first pointer, we remove its link to next node. Using same pointer, we set the link pointer of the preceding node to point to the node that is next to the given node. Finally, using the first pointer, we delete the specified node. Figure depicts the procedure for deleting a node C of a linked list that initially contains letters A, B, C, and D. Traversing a linked list. In traversing a list, we visit each node exactly once. Traversing is performed when we need to access information contained in the nodes of a linked list. Suppose we want to print the list or determine the size of a list, then traversal would be the natural procedure. In order to traverse a list, we normally use a pointer, which is initially set to point to the first node. After the first node has been processed, the pointer is set to move to the second node by using the link pointer of the first node. This process is continued until a node is encountered with link pointer containing a null value. We have already seen the use of traversal procedure in performing insertion and deletion. Figure shows another example of traversal algorithm. The code implements a method lSize, which returns size of a list with pointer head pointing to the front element. Briefly, these steps are involved. A counter is initialized to 0. A node pointer temp is used to point the first node. A loop is set up to scan the list. In each cycle, the counter is incremented by 1. At the end, the function returns the count value. Sorting a linked list. Sorting is another important operation which is sometimes required to be performed on a linked list. In order to sort a list, we systematically compare the contents of a pair of nodes and swap them if necessary to bring them in the given order. The important point to bear in mind is that only information fields of the nodes are exchanged. The link pointers of the corresponding nodes remain undisturbed. Figure lists the code for the sort method. Briefly, it performs these steps. Two node pointers, P and Q, are used to identify a pair of nodes. A nested loop is used to perform comparison and swap the elements to bring the node values in ascending order. A temporary array T is used to hold a data value to be swapped. Searching a linked list. We can perform a linear search on a linked list. In this operation, we start with first element of the list and systematically compare the contents of nodes with the value to be searched for. The operation is terminated when a match is found. If the list is already sorted, the search process can be abandoned after the node value is found to be greater than the value to be searched. If the list is not sorted, we would need to scan the list up to tail node. It is emphasized that unlike an array, the elements of a linked list cannot be accessed directly. Thus, an efficient sorting method called binary search, which uses a middle element, cannot be applied to a list. In the case of the list, there is no simple way of finding middle element. Performance of linked list operation. We now examine the time efficiency of the common operations associated with a linked list. We assume that the list consists of n nodes. Remember, in insertion and deletion operations, we simply readjust the link pointers. The information portion of a node is not affected. The modification of link pointers is not an expensive operation because no movement of stored data takes place. The efficiency of the operation depends on the number of times the list nodes are traversed. When a node is inserted at the front, running time does not depend on the size of the list. Thus, the operation has running time O1. If a node is inserted at the end, the nodes would need to be scanned n times, and at each step, one comparison of link pointer is made. As such, the running time of operation for inserting a tail node is On. If a middle node is inserted on an average of n/2, comparisons of the link parts will be made. Thus, efficiency of inserting a middle node is O(n/2) or equivalently On. The deletion operation essentially involves the same steps as with the insertion, except that two pointers are used. Thus, in general, two comparisons are made. The deletion of a tail node has efficiency O(n), or simply ignoring the multiplicative factor. In sorting a list, we use two nested loops. The outer loop is performed n times. In each iteration, we compare the pointers and set the next value for the index of the inner loop. In general, n-1 comparisons are performed in first iteration, n-2 in second iteration, and one comparison in the last iteration. Thus, altogether, the number of comparisons is as shown. The sort operation has time efficiency or equivalently. Advantages and disadvantages of linked list. The linked lists have several advantages over other data structures for storing data collection. In the light of preceding discussions, we can say that a single linked list has these merits. The size of storage space can be adjusted dynamically at runtime according to a particular application requirement. The insertion and deletion operations are comparatively fast because, unlike an array, the movement of data values within the storage cells is not required. Instead, only the pointers are readjusted. List traversal is extremely fast. The disadvantages associated with a linked list are: a linked list has an overhead of pointers which occupy additional storage space. The elements of a linked list cannot be accessed directly. Instead, one needs to scan the list in order to reach a particular element. Application of linked list. Linked list data structures are normally used to implement other complex structures such as trees, graphs, and heaps. Linked lists are also useful for creating dynamic stacks and queues. These topics will be covered in the subsequent units. Some compilers use linked lists to store and process polynomials. A polynomial is an algebraic expression in which powers of one or more variable appear in a summation. We consider a simple polynomial with a single variable. We can store the coefficients and associated power of variable into a node of a list. The nodes point to the subsequent elements of the expression. Figure shows an example of polynomial and the corresponding linked list. Notice that missing terms of polynomial are not considered in the representation. Using a linked list representation, a compiler can effectively perform the basic algebraic operations on the polynomial values. We can also use a two-dimensional arrays to handle polynomials. Figure shows such a representation. Observe, however, that missing elements in the polynomial must be explicitly represented in the array, because the array data structures does not by itself identify the next element. Array representation is not suitable when the polynomial is sparse, that is, when the polynomial has many missing elements. For example, the expression shown in figure requires just 3 nodes. Against this, a two-dimensional array would require 102 elements, most of which would contain zeros. Cursor implementation of linked list. The linked lists are normally implemented by using pointers or references to the storage location of the linked nodes. In C, C++, the reference pointers are explicitly coded, whereas in Java, implicit references are used. These implementations are often referred to as reference-based. However, some programming languages such as Fortran and Visual Basic do not support explicit or implicit pointers. It is nonetheless possible to use array data structure to implement linked lists. This approach is called cursor implementation. In the alternative method, two arrays are used to store the information fields and pointer fields. The pointer values are, in fact, the indexes of the information fields. By convention, -1 represents the index value for the tail node of the list. Figure shows an example of the cursor implementation of a sample list which contains characters A through H. The data array holds the characters. The second array, called pointer array, contains the indexes of the next elements in the data array. A variable front is used to identify the first element of the list. By using this information, we can traverse the data array and list all the elements. The corresponding linked list is also shown pictorially. Note that the elements of the array are sorted. A major drawback of array implementation is that size of list cannot be increased dynamically. Variation of linked lists. The linked list data structure that we have studied so far is known as regular list. There are several variations of the basic form of list which are useful in different situations. Some common types are circular linked lists, doubly linked lists, circular doubly linked lists, list of linked list or multilist. We now briefly examine the salient features of these data structures. Circular linked list. We have seen that in a regular linked list, we can traverse the nodes in one direction. We cannot go back to any of the preceding node unless we retrace the head node. This is a major drawback. A circular linked list overcomes this limitation. In this structure, the link pointer of the tail node is modified so that it points to the front node. The modified structure is referred to as circular linked list. In this data structure, we can continuously scan the list so as to reach any of the nodes. A circular linked list has no front or tail node. However, in order to make entry into the list, we need to reference one node using an external pointer. As with the regular list, this pointer may be referred to as head pointer. When the list is empty, the head pointer contains a null pointer. Figure shows an example of a circular list containing characters A through F. A circular linked list can be used to represent processes which are executed in cycles. For example, an operating system might use a circular list for round-robin scheduling of tasks. As with regular lists, we can perform basic operations of insertion and deletion on a circular list. Advantages and disadvantages of circular linked list. A circular linked list has these advantages over the regular linked list. Any node can be designated as the first node in the list. Each node is accessible from any other node. A circular linked list is more suited to process strings using concatenation and splitting operations. A limitation of the circular list is that unless the starting node is properly tagged and identified, a traversed operation might go into an infinite loop. Basic operations on doubly linked lists. The basic operations that can be performed on a doubly linked list include insertion, deletion, traversal, sorting, and searching. Their implementations are similar to the ones for regular lists. A significant difference is that in scanning the list, we can perform bidirectional traversal. Also, we need to make adjustments of left and right link pointers. We briefly examine the insertion and deletion operations. Inserting a node into doubly linked list. A new node can be inserted at the front, in the middle, or at the tail of the list. The procedure for inserting a front or tail node is similar to the procedure for a regular linked list. We create a new node. This node is linked to the pre-existing front node or tail node by readjusting the left and right pointers. A similar procedure is followed to insert a node in the middle of the list. We use a pair of temporary pointers to scan the list. The second pointer trails behind the front pointer. Thus, when the scan pointer points to the given node, which will be preceded by the new node, the second pointer points to the immediate predecessor of the given node. After the given node and its preceding node have been identified, the link pointer of these nodes are adjusted to link them to the new node. Figure illustrates the insertion procedure of the original list, which consists of nodes containing letters A, B, C, D. A new node Z is inserted before the node containing letter C. You may wonder why we need two pointers when a link to previous node is already known. Actually, although we can access a preceding node, we need an external pointer to make adjustment in the link pointers. Deleting a node from doubly linked list. In order to delete a given node, we first locate the node. Then, the link pointers of the succeeding and preceding nodes are adjusted to break links with the given node. The deletion process is illustrated in figure. The original list contains characters A, B, C, and D. The node C is removed from the list. Advantages and disadvantages of doubly linked list. The main advantages of a doubly linked list are: it allows a bidirectional traversal for processing nodes. Insertion and deletion are fast. A sorted list can be printed in either ascending or descending order. The major drawback of a doubly linked list is that additional storage space is required for the link pointers. Also, the address of the preceding and succeeding nodes needs to be closely tracked to avoid misdirected traversals. Circular doubly linked list. A circular doubly linked list is a variant of the doubly linked list. As the name implies, in this data structure, the next link pointer in the tail node contains pointer to the first element. Also, the previous link pointer in the first node points to the tail node. An example of a circular doubly linked list is shown in figure. Since there is no first and last node in a circular list, we choose an arbitrary node for making entry into the list. An external pointer identifies this node. A circular doubly linked list inherits all the advantages of a circular and doubly linked list. We can access the nodes from a given node. Further, we can traverse the list in forward and backward directions. The disadvantage is that the link pointers need to be closely monitored to avoid the risk of endless looping through the list. Multi-list. We can combine a set of related list structures into an integrated linked list called multi-list. In this way, we can easily access all the nodes in one list that are related to given node in the other list. Consider, for example, a list that contains student records and another list that contains subject information. We can combine these lists into a multi-list so that we can access all the students that are registered in a given subject. Conversely, we can access the subjects in which a particular student is registered. In order to build the multi-list, we need additional link nodes that link students with subjects. Thus, the list would contain these nodes. Nodes that contain subject data and link pointers for subject. Nodes that contain student data and link pointer for student. Link nodes that connect subjects with students. An example of the multi-list is shown in figure. The subject and student links are circular. The labels std1 and std2 and so forth are head pointers to student links to the subjects. Likewise, sub1 and sub2 and so forth are head pointers to subject links to the students. It is assumed that each student can register in 2 courses. As shown, the first student is enrolled in the first and the third subject. Observe that a multi-list can be traversed to list students by a given subject or the subjects taken by a given student. Introduction.